Hi folks, this video is about the laws of logarithms, or more specifically just one law, and that is going to be our product law. So if we think back to exponents, we have a scenario where we have a base to an exponent multiplying that same base to a different exponent. So if our bases are the same and these numbers are multiplying each other, we get to add the exponents. So for example, x squared times x cubed is x to the power 5. Likewise, we do the same thing down here. So x to the power 7 times x to the power negative 4. So 7 plus a negative 4 is x cubed. So this is really an exponent law. There's also a logarithmic law for this situation. So the logarithm of some argument where that argument is a product, we can actually split that logarithm into two separate logarithms of each factor of the product. So log A b times c becomes log AB and log AC. So we separate them out into their separate logarithms. Now, just like we can see that we separate them, we can also combine them. So we make two logarithms one. So if two logarithms are separated by addition, again, the bases of the logarithm have to be the same, then we can write it as a product over here. So that's what we're going to do in this next line. We have log base 2 of 5 and log base 2 of 6. The bases are the same. So we can combine the arguments with multiplication. So we get log base 2 of 5 times 6. That's multiplication dot. Or log base 2 of 30. Same idea in our second example. The base of the logarithms are the same. So then we have to multiply the arguments. Log base x of 3 times 7, if you prefer writing it that way. And then 3 times 7 is 21. So log base x of 21. And you might be asked to prove the product law at some point. So we're going to run through that right now. The starting point for our proof is just a couple of definitions. So log base a of m is equal to x. That's just what we're setting up. And log base a of n is equal to y. Now what we can do is we can write both of these in exponential form. So to do that, we move that a to the other side. So we have m equals a goes to the other side, a to the power x. And to do the same thing with our second equation, that would be n equals a to the other side, a to the power y. So next thing I'm going to do is I'm going to say m times n is equal to, well, m is a to the power x, and n is a to the power y. So m times n is a to the x times a to the y. Now using the exponent rule we had before, we know when we're multiplying two numbers together that have the same base, we can add their exponents. So mn equals a to the power x plus y. Then I'm going to write this in logarithmic form. So I'm going to move this a over to the other side. So we have log base a of m times n. And that just leaves me with x plus y on the right-hand side. Now, right at the very start of our proof, we just started with a couple of definitions. We say that x is log base a of m. So I can replace that with this x here, or replace that x with log base a of m. So my left-hand side doesn't change. This x becomes a log base a of m plus, and we have this y, but I can replace y as well. Log base a of n, and that is our product law. So we're going to apply our knowledge now a little bit, and I encourage you to pause the video and try these on your own before I go through each answer. So first one, log base 4 of 8 plus log base 4 of 10. So right as a single logarithm, I have to combine these two. When two logarithms are being added, that means we can multiply their arguments. So log base 4 of 8 times 10, log base 4 of 80. Now the second one, and it's the same setup, we just don't have numbers, we just have variables this time. So the base of the logarithms are the same, they're separated with addition, which means we get to multiply the arguments. So log base x of a times b. And that's as simple as I can make it. Now we're going to get to solve a couple of logarithms. Seeing as we just went through the product law where we can separate these, I'm going to separate these into two separate logarithms. So log base 3 of 27 plus log base 3 of 3. So I'm separating the argument with addition because they're being multiplied. Then I'm going to solve each piece independently. So I'm going to say that log base 3 of 27 is equal to x, and log base 3 of 3 is going to equal y. So that really means I have x plus y here. So to solve for x, I'm going to put this in exponential form. 27 equals 3 to the power x. And if I have an exponent over here, or exponential number here, I want to write this with the same base. So 27 is 3 to the power 3. So 3 to the power 3 is 3 to the power x. If the bases are the same, then the exponents are going to be the same. So 3 is equal to x. Similar idea over here. So I'm going to put this into exponential form. 3 equals 3 to the power y. Now, we have an exponential number here. We want the same base. Well, they have the same base, and there's just kind of assumed 1 to be there. So we have 1 equals y. And fun fact for you, anytime the base of a logarithm and the argument of that logarithm are the same, you're always going to end up with a 1 there. So in terms of our x plus y here, x is 3. So x plus y is my continuation from up here. X is equal to 3, y is equal to 1. So my answer is 4. Let's do the same thing with our second example. So I'm going to separate this into two logarithms. Log base 2 of 0.25 plus log base 2 of 64. So I'm going to say x is equal to log base 2 of 0.25 and y is equal to log base 2 of 64. So really what I'm looking at is x plus y. So to solve for x, I'm going to put this in exponential form. 2 to the power x equals 0.25. And I'd find it a little more useful to write this as a fraction. So 2 to the power x is 1 over 4. And then I can actually write 1 over 4 as 1 over 2 squared. And if I just want to get rid of this fraction, I can write this as 2 to the power x equals 2 to the power negative 2. Now that my bases are the same, I can see that x is equal to negative 2. In the right-hand equation, we're going to solve for y, so I'll move the 2 to the other side. 2 to the power y equals 64. And then we need to write 64 with a base of 2. So 2 to the power y equals 2 to the power 6. Now the bases are the same, so y equals 6. So returning to this x plus y line here, I'll move this down slightly. X we said was negative 2, y we said was 6. So again, we get an answer of 4. one more question to run through. We're given log base 7 of 45 is equal to 1.956, and log base 7 of 0.5 is 2.646. We're asked to solve log base 7 of 45 times 0.5. So we're basically going to do the same thing we did before. We're going to separate this into two separate logarithms. But now we're given some information here. So we could do the same thing we did before. We could say that x is equal to log base 7 of 45 and y is equal to log base 7 of 0.5. But when we put this into exponential form, 7 to the power x equals 45, we won't find an integer number for x. So when we put this into exponential form, we won't be able to find an integer number for x because 7 squared is 49, so that's too high, and 7 to the power 1 is 7. So obviously the answer is going to be between 1 and 2, closer to 2, but I can't accurately guess what that's going to be. So luckily with this information, I can just sub this in. So log base 7 of 45, which is this piece here, is 1.956. Then log base 7 of 0.5 is 2.646. So then we just need to do a little bit of arithmetic. And our answer is 4.602.